Okay, so I started the recording. It's good. We have more people today compared to last week. So, okay, what we did last week, for those of you who attended the class, and I hope the rest of you watched the video, is that, of course, in the general, under the general topic of boundary layer theory, basically what we're doing is, what we did is we, starting from the Navier-Stokes equations, we performed an order of what we call an order of magnitude analysis. I mean, what that means is actually we investigated the terms in the Navier-Stokes equations one by one, and keeping in mind the fact that boundary layers are actually very thin, very small. So the boundary layer thickness delta compared to the characteristic length of the solid object, like the chord of an airfoil, for example, this delta is quite very small compared to the C, for example. Then keeping that in mind, and by working on the non-dimensionalized version of the equations, we try to compare which terms are, more or less at the same order of magnitude, which terms are at a smaller or a much smaller order of magnitude. So this is called an order of magnitude analysis. So after doing that, we saw that the original Navier-Stokes equations are a little bit simplified. And what you're seeing on your screen is that simplified version, which we call boundary layer equations. And these boundary layer equations, what you're looking at on the screen is for 2D flow. As you can see, it's only written in terms of U and V velocity components. It is for compressible flow. Rho may not be a constant, but at the same time, it's for a steady state flow. So there's no time derivative terms in the equations. So as you can see, for example, the continuity equation, again, just to remind you from last week, the continuity equation in the first row, so this one here, is basically the same. After order of magnitude analysis, it's the same equation. The X momentum equation, this one, it is modified in two ways. The bound in the after order of magnitude analysis. The first is the fact that we have the pressure gradient. This is the pressure at the edge of the boundary layer. That's why we have a subscript E here. Because of the Y momentum equation, actually, Y momentum equation says P pressure is independent of Y. So the gradient is actually zero. Since in a two-dimensional flow, if it is independent, mathematically independent from Y, which means that it is only a function, it can only be a function of X. So this derivative turned out to be an ordinary derivative instead of a partial derivative. And plus, we lost one of the terms regarding the viscous terms here after order of magnitude analysis. So X momentum equation gets modified a little bit. Y momentum equation is basically almost lost entirely except for this term. And the only thing is this term is left, and this term says the pressure gradient along Y direction, and we try to explain it here, up here, and is zero. So pressure does not change across the boundary layer. Let's say if it's a flat plate, let's say normal to the surface. And similarly, energy conservation equation is here. And in order to have a closed equation set, we need to add the equation of state and enthalpy definition so that we obtain a closed set of equations, which we call the boundary layer equations. So simplified form of the Navier-Stokes. Now, of course, in order to solve this equation set, we need boundary conditions. So these are the boundary conditions. Of course, we know them. At the wall, at y equal to 0, velocities are 0, u and v are 0. That's what we call the no slip condition. And temperature must be equal to wall temperature. So that's the wall condition. And as y goes to infinity, as you approach to the edge of the boundary layer and beyond that, u becomes equal to u edge, t becomes equal to t edge, especially for a flat plate. That is true. So we obtained these equations last week, and I told you last time that now the next thing is, I mean, the question is, if we have this set of equations subject to this boundary conditions, can we actually have or obtain solutions for these equations? The solutions will give me some kind, if I can solve them somehow. For example, it will give me how the boundary layer grows on top of that solid object, the delta variation, delta star variation, theta variation, the displacement thickness and momentum thickness variations along the body, plus, for example, I can get the velocity field within, or the velocity variation function within the boundary layer. If I know that, I can actually calculate wall shear stress, which is related to the velocity gradient at the wall. If I know wall shear stress, I can calculate friction coefficient. If I know friction coefficient, I can turn it into the drag coefficient. So therefore, using the solutions of boundary layer equations, I can obtain all that. So after, actually, the guy who actually performed this order of magnitude analysis was Prandtl and his students, early 1900s. And then his doctoral student, PhD student Blasius, in his thesis, PhD thesis, came up, first time attempted to obtain a solution to these equations, of course, under simplified, even more simplified conditions. So today we will learn this. We will learn what Blasius did almost 120 years ago in his PhD thesis. So today we call it Blasius solution. So this is very fundamental in aerodynamics to learn this. And then we will, afterwards, in the coming days, we will see if we relax some of the assumptions, additional assumptions that Blasius introduced to be able to solve the boundary layer equations. If we relax some of them, if we get rid of some of them, how we can actually get better, let's say, more realistic solutions. But what Blasius did was he first did some assumptions regarding this boundary layer flow. First of all, yes, the flow is assumed to be two-dimensional and steady. So that is already what we had in the above equation set. Second one, the flow is assumed to be incompressible. Okay, so density variations are ignored. So this is going to be therefore valid for low Mach number flows, Mach number less than 0.3. And he assumed constant thermophysical properties. Like what are those, for example? Like viscosity, for example, thermophysical properties. So like viscosity is constant, thermal conductivity is a constant, therefore like Prandtl number is a constant, things like that. And fourth, and probably the most important assumption that he did, is that he assumed this term to be equal to 0. The pressure variation along x, so streamwise pressure variation, is 0. So that term will disappear from the equations. Is this a realistic assumption? Well, in reality, yes. And it can be, this kind of flow field over a solid body can be generated in a laboratory environment, in a wind tunnel, for example. You can do that. The geometry must be basically a flat plate. It shouldn't have any curvature on any of its surfaces, so it should be flat. And you should put that flat plate inside a wind tunnel. And then by, if needed, by properly adjusting the wind tunnel cross-sectional area a little bit, you can actually obtain this condition. You can generate a flow field around this flat plate with zero pressure gradient in the streamwise direction. So therefore, under these assumptions, okay, so let's put the note here. This is basically a flat plate or flow around a flat plate. Let's say flow around a flat plate. So under these assumptions, the equations get simplified even more. So the equations become like this. So since it is incompressible, we lose the raw density terms. So the mass conservation equation looks like this, continuity equation. The momentum equation looks like this, u plus du dx plus du dy is equal to, on the right hand side, the dp dx term is zero, so we don't have that. We only have the viscous term. So second partial derivative with respect to y square. That's basically the x momentum conservation equation, and y momentum conservation equation is still the same, okay? And here, this is the kinematic viscosity, by the way, of course, which is defined as mu over rho. And since it is incompressible flow, the energy and the momentum equations are not coupled. So it is enough to solve only momentum and mass conservation equation to get the velocity field. So the question is, so this is the equations that Blasius came up with for this, let's say, simplified problem with zero pressure, streamwise pressure gradient to the steady incompressible flow. And he attempted to obtain a mathematical solution to this problem. And we will go over step by step how he did that. So the starting point in order to obtain a solution was to assume a coordinate transformation. Assume a coordinate transformation, okay? Such that coordinate transformation, of course, means we define new, instead of x and y are the independent parameters here. Instead of x and y, we define new, let's say, independent variables. And the definitions were a variable xi, which is chosen to be equal to actually x, and the variable eta, which is defined as y times square root u infinity, the velocity, divided by kinematic viscosity times x. Okay, so that was the coordinate transformation proposed by Blasius. I mean, what he is basically proposing is, okay, instead of writing these equations as partial derivatives with respect to x or partial derivatives with respect to y, write the same equation with partial derivatives with respect to psi and partial derivatives with respect to eta, hoping that that will simplify this equation set mathematically, okay? So, of course, then how do I obtain those derivatives with respect to these new variables? First of all, we need to generate that information. So using chain rule, for example, we can obtain, using chain rule, we can obtain some things. For example, what is a derivative, partial derivative with respect to x? It's basically partial with respect to psi times d psi over dx plus partial with respect to eta times d eta over dx. So this is how we do a proper transformation of the coordinate. Similarly, wherever we see partial derivative with respect to y, we need to replace it with partial with respect to psi and d psi over dy plus partial with respect to eta, then the eta over dy. Okay. Of course, we know some things. For example, d psi over dx term, this is actually equal to 1. We know that. What else do we know? We have d psi over dy term. This is actually 0. We know that. And we need to know basically what else do we need to know? For example, d eta over dy. So this term, d eta over dy, this term is equal to square root of u infinity multiplied by nu x. We know that. Yeah. So, of course, we need to know the eta over dx, but it will come in a second. So if you insert these, substitute these in the equations, basically, for example, d over dx derivative, that wherever we see that derivative in the equation, becomes equal to d to the d psi derivative plus d eta dx times d over d eta, and d to the dy derivative becomes equal to a constant u, I mean not a constant but a function of x, I'm sorry, u infinity time u infinity divided by actually eta times x d d eta.
Hocam,
Evet.
in the eta term, is the x is a subscript of nu, or are they in multiplication?
Here,
Yes.
it's multiplication.
Okay, thank you.
It is eta times x. And the second...
Is it eta times or x or viscosity times x?
Let me check. It must be eta times x. I mean, this viscosity times x, I mean, if you multiply eta definition by x, they must be the same thing. Eta is this, right?
Okay.
If you multiply by x, so x square, so it gets canceled. This is mu over rho, and rho gets out and everything. I mean, if you do the cancellations, it must be equal to eta times x. Okay. The second derivative, we also have it on the right-hand side of the x momentum conservation. So this is u infinity divided by, again, eta times x, and second derivative with respect to eta, d square, d eta square. So this is one thing. So there are some, so we obtained some, or obtained corresponding derivatives, derivatives corresponding to dx and dy and d square, dy square, written in terms of d eta, d square, d eta square, and d psi. So let's keep this in mind. So we will substitute these in the equations. But in addition, that's not all. He also defined a stream function. Also, let's write this down. Also, define a stream function psi such that psi is equal to square root of nu times x times u infinity times a function of eta. Okay. Now this expression for as Blasius defined it, this expression for stream function is not, of course, randomly chosen. This expression for the stream function actually, it can be shown that it identically satisfies the continuity equation. For example, how we can check this? For example, if we get the derivative of psi with respect to y, that must be equal to the u component of the velocity, and one can show that this is actually equal to u infinity over nu x times d psi over d eta, and and this can be written basically as u infinity times the d psi over d eta. Eta is only inside this function, so we will call it f prime eta. So f prime means this is only a function of eta, so derivative with respect to eta, ordinary derivative with respect to eta, whatever that function is. Right now we do not know that function. Okay, so we will just call it f function, f prime. Similarly, v component is equal to minus d psi over dx, and so this is going to be equal to d psi over d psi plus d eta dx d psi over d eta, and sorry, this is going to be equal to minus 1 over 2 square root nu times u infinity over x times f minus, if I'm not missing any of the terms, nu times x u infinity square root times d eta dx times f prime. Okay, and one can actually show that this, if this is u and this is v, and if you take the second derivative of the I mean, we need du dx plus dv dy is equal to 0 for conservation of mass. And if you take the second derivative of the string function, you have to take the derivatives of these and add them up, and you can show that this kind of definition automatically satisfies that equation if a string function is defined like this. So this is the second information that Blasius came up with. Now the thing is, let me check. The function f eta here is important, okay? And in fact, we can directly see from here, from this equation, that when we take its derivative, I mean, whatever that function f eta is, when we take its derivative with respect to eta, df d eta, that derivative actually becomes equal to u over u infinity, right? So in reality, the first derivative of this function is equal to u over u infinity. So if for a given u infinity, which is going to be a constant, let's say, for your problem, if it's a flat plate problem, it's the free stream velocity, f prime eta will directly give you the u velocity component within the boundary layer, okay? So that is convenient. So basically substituting all these terms into the momentum equation, we get an equation that is written in terms of this f function, okay? So what do I substitute? For example, I use, if wherever I see du dx or du dy, I will make use of this f function, or basically the stream function definition, and then I will insert these terms into the momentum equation. So x momentum equation, that is. So substituting all above terms, whatever we got so far, into the x momentum equation, it looks something like this. So u infinity times f prime, okay, so I'm not going to write f eta anymore, f prime times u infinity d eta dx f double prime minus 1 over 2 square root of nu u infinity x f plus square root of nu x u infinity. This is not a subscript. This is multiplication by the x coordinate. D eta dx times f prime times u infinity times u infinity over nu x. We will simplify this equation in a second. And this must be equal to nu times u infinity times u infinity over nu x f triple prime. So derivative of f function with respect to eta 3 times, so third order derivative. So we simplify this equation because we can collect many of the constants multiplying with each other. We have many of these constants. If we simplify from the left and right hand side of the equation, after simplification, let's say, after simplification, which means that we are regrouping some of the constants and they will cancel out with each other, we get this equation. We get 2 times f triple prime plus f times f double prime is equal to 0. Okay, this is known as the, today we know it as the Blasius equation. Okay, what does this equation represent physically? It represents basically all three. It is one equation, first of all. Mathematically, it is only one equation. We have reduced our original, we started with originally 3 partial differential equations, the conservation of mass, x momentum, and y momentum equation. Now, after applying this mathematical transformation, plus after applying this definition of the stream function, this 3 partial differential equations set is reduced to one single equation, and not only that, it is an ordinary differential equation. It's not a partial differential equation anymore. Okay, because wherever f is only a function of eta by definition. So wherever we have primes, it means that this is the second derivative of f with respect to eta. This is the third derivative of f with respect to eta. That's it, and it's only a function. It's only written in terms of ordinary differentials with respect to f, and it's only one single equation. It is subject to it can, therefore and it is representing the full physics, meaning conservation of mass, x momentum and y momentum conservations around a flat plate with 0 pressure gradient for steady incompressible flows. So it is representing the full physics around it analytically. So the question is, how do we solve this equation now? Of course, we need to know some boundary conditions. Now, based on our coordinate transformation at eta equal to 0 now, this is a function of eta, which corresponds to our wall condition at y equal to 0. We have f equal to 0 and f prime actually equal to 0. And also, as eta goes to infinity, y will also go to infinity, and f prime therefore will be equal to 1, because f prime is equal to u over u infinity. Don't forget that, u over u infinity. So u will, at the edge of the boundary layer, will reach to u infinity or u edge condition, but for flat plate, u edge and u infinity are equal to each other. So f prime will automatically go to 1. So on the surface, u is 0, so f prime is equal to 0, and plus eta is also 0. Not only u is 0, eta is also 0. So, since f is a function of eta, so it will be automatically 0. So subject to these boundary conditions, and we have this one single ordinary differential equation, we see that it's a third order non-linear, though, by the way. I did not mention that, but we multiplied f we multiply f with f double prime. So it is indeed nonlinear equation, third order nonlinear ordinary differential equation. So it can indeed be solved by standard techniques. I mean, different techniques. So very simple numerical integration can be done for this. I mean, like Runge-Kutta method, for example, we can apply that. And what we do is we start integrating this equation at the wall and slowly move towards positive y direction or positive eta direction, therefore, in small increments of delta y. And then we slowly integrate this equation. Just let's put a quick note here. Methods like, I don't know, did you guys take the numerical methods class? Maybe you already had a homework or something regarding the solution of Velasius equation. Sometimes Ismail Hoca gives this homework. So, or I don't know if you never did that. Methods like Runge-Kutta integration can be used. Other methods can also be used. Okay. And when we do the integration, we basically obtain a solution within of, basically for the velocity profile inside the boundary layer. So velocity profile inside the boundary layer of a flat plate, basically that is exposed to U infinity. The solution can be drawn if this is f prime eta, so basically U over U infinity axis. And if this is the eta axis, and let's write the definition of eta here again, it's y times square root of U infinity divided by nu times x. Okay. So this indeed looks something like this. At y or at eta equal to 0, this is 0, and then this actually finds a function that looks something like that. Okay, and let's say at the edge of the boundary layer where we reach the free stream condition, this corresponds to an f prime eta value of 1. Because that's how we define that. And basically during the integration, you can, we integrate this, piece by piece. You divide this into small delta eta increments and then integrate numerically, piece by piece and reconstruct this profile. Now, this profile that we obtain, this velocity profile, indeed, as I said, indeed corresponds to the actual flow field. Maybe let me draw it to the right a little bit. Let me shift it to the left here. Flow field around the flat plate for a steady incompressible flow. I forgot to mention one thing. It corresponds to also steady incompressible laminar flow. So there's no turbulence involved. We haven't really seen anything about turbulence yet, but we will see that very soon. So basically, if there is some kind of boundary layer, I don't know, growing, on top of this flat plate, when it exposed to some U infinity, wherever we get, wherever you want to know the velocity profile, let's say at two different stations along the boundary layer. Okay, normally if you go to the wind tunnel, put this flat plate and measure these velocity profiles, if they are at different locations, let's say this one is at x1 away from the leading edge, this one is let's say x2 away from the leading edge, so you would obtain a velocity variation at x1 with at x1 location, so velocity will change with y. At x2 location, you will have probably a slightly different variation with y. However, the solution that we get from Blasius is, first of all, a generalized solution, and it is indeed the same as plotted with respect to these new coordinate system eta and f prime eta. This profile is universal, so this does not change wherever you go in the x coordinate system. So if whether you are here in the at x1 location or whether you are here in the x2 location, this eta versus f prime eta graph, let's say f prime eta, is still the same. It's always the same. Okay, but starting from this, therefore, kind of universal function for velocity profiles, by appropriate dimensionalization or appropriate, let's say, reconstruction of the original coordinates, you can generate this profile. Also, you can generate this profile at different locations. So therefore, f prime eta is u over u infinity. So we can say variation of u with eta does not change. This is the same for all stations, for all x stations, let's say. Okay, and again, valid under the assumption of Blasius solution, meaning that we have a steady two-dimensional flow, dp dx is zero pressure gradient, and it's laminar flow. So let's write them down again. Laminar flow, there's no turbulence involved. That's another story we will see later. If the boundary layer is laminar or turbulent, and we will see what we mean by laminar flow and turbulent flow a little bit later. But laminar 2D steady incompressible flow around a flat plate. This is therefore full analytical solution. Well, I mean, the equation is analytical ordinary differential equation. The solution, it can be solved analytically as well. Here, we just propose the method to solve it numerically. Flow around a flat plate, which means dp dx is 0. Okay. So therefore, we indeed have a velocity profile. Okay. So this function is indeed the velocity profile. And the nice thing is, once we know the velocity profile, we can do lots of stuff. Okay. We can do lots of stuff because many boundary layer parameters that we have learned so far, like, for example, those definitions of delta star, definition of theta, and wall shear stress even, and so therefore friction coefficient, everything depends on this velocity distribution. So therefore, once we have a function for the velocity distribution, we can obtain all these boundary layer parameters. And not only that, for example, we can estimate the drag coefficient from this obtained velocity distribution. And we will actually start seeing that. Let me quickly organize my notes. I think I mentioned many of it. Okay, so let me zoom out a little bit. So let's do that, meaning how we can actually make use of all of this information that we generated, or that Blasius generated in his PhD thesis after this solution. For example, one thing that we are interested in is, as of course aerospace engineers, we want to know the drag coefficient. And drag coefficient, we know that it is related to the shear stress at the wall. We call it tau wall. Yes, and tau wall, we know that it can be calculated by viscosity times the velocity gradient at the wall, du dy at the wall. And since we have now, so wall meaning y equal to 0, since we have now the velocity function, we can indeed have an expression for the wall shear stress. And not only that, this physical quantity, which is du dy, we know that it will be changing along the flat plate. It is a function of x, but what will be not changing will be the derivative of u eta with respect to eta, for example. Okay, so that will be constant, but I can convert it to d dy variation along x. So basically, I can obtain the variation of tau wall with x, so tau wall x, for example, so that I can do many things. I can start integrating wall shear stress, and in fact, go towards getting the drag coefficient in reality. So for this calculation, for example, we need du dy at the wall, and we can show that this is actually equal to u infinity times df prime dy at the wall, and so this is u infinity times u infinity divided by nu times x df prime d eta. Okay, so, and this is simply the second derivative. So u infinity times square root of u infinity nu times x times the second derivative of this function. So this is one example. The nice thing is today, if you, I mean, not today, it's been there over maybe past 40 years. Many people, of course, solve these equations. I'm not sure if it's at the back of your aerodynamics book. It is probably there, but all these function values are listed generally in tables. For example, f value, f prime value, and f double prime value. These are all listed in different books. Okay, I'm not sure if you have these lists in your aerodynamics book, but for in any boundary layer related book, for example, in the famous book by Schlichting, which is written in 1979, the books, this is kind of considered to be the Bible of boundary layer theory, which is the book's name, boundary layer theory. For example, in that book, you can find tables that list f prime and f double prime values. So basically what we need here is that f double prime value at the wall. So we need f double prime 0, okay, value from that table, so that we can find out the wall shear stress. Therefore, will be equal to viscosity times u infinity times square root u infinity divided by kinematic viscosity times x. So here comes the x dependence times the second derivative of f function evaluated at 0, which comes from table, listed table. So for a Blasius boundary layer, sometimes we call it that, this specific boundary layer that we have been discussing in the first hour of this class, sometimes it's called the Blasius boundary layer, so that the wall shear stress distribution within that boundary layer can be obtained from this function. So you need to know the dynamic viscosity, the kinematic viscosity, free stream velocity, and square root of x, 1 over square root of x dependence. You can see that, and whatever this numerical values you get, you multiply it with all that. Before we give a break, we know that as I was trying to explain to you, wall shear stress is related to surface friction, okay, and in fact related to what we call friction coefficient, okay, and this friction is related to the fact that we are dealing with the viscous flow happening over this flat plate. So we can now estimate the friction coefficient, and in fact the definition of friction coefficient is tau wall divided by 1 over 2 rho infinity u infinity square. So if I just divide all these terms by 1 over 2 rho u infinity square, so I have 2 times mu I mean, I am writing here rho infinity, but we are dealing with incompressible flow, so it's, you know, that it does not change. So it's actually rho. Anyway, so u infinity square times u infinity multiplied by u infinity divided by nu times x times the second derivative of the Blasius function evaluated at 0. So if you make the necessary cancellations in these terms, we get an expression for CF. And of course, after inserting the numerical value of f double prime 0, this is equal to 0.664 square root of Reynolds x. And here Reynolds x is, and this is a subscript, Reynolds x is defined as u infinity times x over nu. So this equation tells you how friction coefficient varies along the flat plate that is immersed in a laminar flow that has basically a laminar boundary layer on top of it. And this is the solution, how CF friction coefficient changes with X or changes with Reynolds number. For example, let's say just a quick example, then we will give a break. Let's say we are dealing with a certain flat plate that has a chord length of C. Okay, okay. So in order to obtain the full, I mean, when you, first of all, at every X location, by the way, this is the X coordinate, at every X location, as you can see, you will have a CF value. So CF will have a certain distribution here, right? As you increase X, or as you move from the leading edge to the trailing edge, X will increase, Reynolds X will increase, and therefore CF will be basically a function of X. At every X location, you will have a value. And if you integrate it with X from 0 to chord, 0 to C, that is basically going to be your drag coefficient. And what is the what will be the value, for example, of the friction coefficient at the trailing edge, which means that you just need to insert C here in terms of X chord length, and then calculate this, and then calculate this, and then from theory, Blasius's boundary layer solution, you directly get a CF value, for example, at the trailing edge of your flat plate. So this is, I'm telling all this to show you how useful this is. Once you obtain an expression for the velocity profile, then basically you are set. Okay, and Blasius was able to obtain it for this kind of simplified case. Okay. Well, let's give a 10-minute break.
Hocam,
So,
may I ask something before the break?
Sure.
Can you possibly extend the due date of the lab by 1 or 2 days?
I have to consult with Mustafa Hoca and assistants. Okay.
Because a lot of assignments and reports kind of.
When was the due date?
Friday.
This
midnight.
Friday?
Yes.
This Friday. Okay. I will talk to them.
Okay. Thank you, sir.
Good. Let's give a break, and I'll see you in 10 minutes. Okay. So as a part of this Blasius solution, now we indeed have an expression for the friction coefficient, and we can relate it to the drag coefficient. We will do that actually right now, and then we can also obtain expressions for the other parameters, boundary layer characteristic parameters. Now, if you would like to obtain the overall friction coefficient over the full plate, so as I was saying in the previous hour, this CFX is changing. It's a function of x, so CF value is changing with x. But if I would like to calculate, for example, an average CF value calculated overall the full plate, actually this will be the drag coefficient or viscous drag coefficient of this flat plate. This can be obtained by integrating, as I was saying in the previous hour, from an averaging from 0 to C of this CF distribution. This CF distribution, and this can be called the overall or average skin friction coefficient. Skin friction coefficient, and just need to do this integration here. So this is 1 over C from 0 to C, and we insert the value that, I mean, the expression that we get from Blasius solution divided by square root of Reynolds x. So U infinity times x over nu and integrated with dx. When you do that, the expression that we get for the average skin friction coefficient for the whole flat plate will be equal to 1.328 divided by basically Reynolds number based on chord. So Reynolds number based on chord is simply U infinity times chord of the flat plate divided by the kinematic viscosity of the fluid. Okay, so this equation gives you a direct estimation of that. I mean, if you know at which Reynolds number your flat plate is operating, meaning that you need to know U infinity and you need to know how big your flat plate is. And you can calculate Reynolds C and get the square root of it, or 1 over square root of it multiplied by 1.328, and you have your full friction coefficient estimation, or theoretical value for the full friction coefficient for the whole flat plate. Now, similar to what we did here, we can also obtain expressions for the boundary layer thickness, for example, delta or the delta star, and and also theta. For example, let's say concerning delta, which we defined as the boundary layer thickness before, we can basically say that, of course, how did we define delta before? We said delta is where we have U is equal to 0.99 of U infinity or U edge, and U over U infinity, as we know, is F prime eta. So this means that F prime eta must have a value, or F prime must have a value 0.99. At that location, we will call it the boundary layer edge, or boundary layer edge where we have the boundary layer thickness. This from the tables, actually I found the tables in the break, but I have to locate them again. Maybe I will do that in a second. If you look at the tables, wherever you reach F prime equal to 0.99, this happens around eta equal to 5, okay, approximately equal to 5. So therefore, basically from here, we can calculate the delta value, the boundary layer thickness at any location. How? Because using the eta definition, eta is equal to y times square root of U infinity divided by nu times x. So instead of y here, we can put, you know, the y value at U equal to 0.99 U infinity. So it will basically be delta. So this is going to be delta times square root of U infinity divided by nu x. But this from the table, for the Blasius solution, it says that this must be equal to, let's say, 5. And from here, then we get an expression for delta growth for a Blasius type boundary layer. So this will be equal to 5 times x divided by square root of Reynolds x. Okay. And we notice one important result from here is that the boundary layer growth, so delta is a function of x, as you can see. The boundary layer growth actually happens proportional to square root of x. Okay. But don't forget that this is the case of a laminar boundary layer. Laminar boundary layer. So for a flat plate laminar boundary layer, the thickness of the boundary layer grows with square root of x. So x starts with 0 at the leading edge, and as x increases, boundary layer thickness will grow. At every x location, it will grow proportional to the square root of x and reach a certain value at the trailing edge, where x will be equal to the chord, and you can actually estimate the thickness of the boundary layer at the chord if you just insert the chord value, a physical chord value of your real flat plate. As long as it's operating in a laminar boundary layer regime, if it does have a turbulent boundary layer regime, we will actually have a thicker boundary layer, and we will actually obtain solutions also for that in the upcoming classes. And those solutions will not be equal to this. The solution will be a slightly different equation, resulting in a thicker boundary layer thickness value at the trailing edge. So what else? Another parameter, of course, we are interested in is the displacement thickness, because we use the displacement thickness, as we have seen last week, for example, generating an effective body and implementing like a hybrid implicit viscous solution and everything. So we need the delta star value. And that delta, using the delta star definition, let's remember that this was equal to 1 minus u over UH times dy, and assuming rho is a constant, so for incompressible flow. So here we have an expression for u obtained from Blasius solution. So we use that. So this will be equal to u infinity times x divided by, I'm sorry, not u infinity, nu times x, nu times x divided by u infinity, and then now integrated from 0 to eta, some eta value instead of y1, let's say eta 1, and then 1 minus f prime eta d eta. And then when we do this integration, we get, this is going to be equal to square root of u infinity, I'm still making the same mistake, nu times x divided by u infinity multiplied by eta 1 and minus f at eta 1. Okay. And from the tables, one can note that from the tables for f eta, okay, one can note one important concept. The value eta minus f eta is always equal to 1.72 for all values of eta above 5. So when we are above 5, if you remember a few minutes ago, we said that we are basically outside the boundary layer. So eta equal to 5 is kind of the edge of the boundary layer. When we are above 5, we're outside the boundary layer, and this term actually does not change anymore. So using this information from the table, we get an expression for delta star, and this is equal to 1.72 x divided by square root of Reynolds x. So as you can see, let's start, let me zoom out, try to compare it with the delta variation, the delta star versus delta. Again, first of all, delta star also grows with square root of x, proportional to square root of x, but the constant is different. As you can see here, one constant is 5, delta star constant is 1.72. Okay, and our final, or the last but not least, the third boundary layer characteristic parameter is the momentum thickness, theta. Momentum thickness, theta, and our definition for theta, and I'm not going to repeat all physical meanings of delta star and theta, but we have discussed this quite a bit. So this was for incompressible flow, this is equal to U over UE times 1 minus U over UE dy, again for rho constant. So we insert the U value we obtained from Blasius solution. Anyway, I'm not going to do the exercise now the third time, but what we get is this is going to be equal to 0.664 x divided by square root of Reynolds x. Okay. So basically what we obtained is we got the full boundary layer characteristics based on the Blasius flat plate boundary layer solution. We got the delta variation, delta star variation, and theta variation. All of them, all of these three are growing, let's say, as we move away from the leading edge of the flat plate, moving in the streamwise direction. They all grow proportional to square root of x location, which is the location away from the leading edge, but at different rates. As you can see, their constants are different. So at any location x, delta star, and theta values will be different. Plus, we have already seen how we can actually estimate the drag coefficient based on friction coefficient, which is based on wall shear stress, using the velocity field that we obtain basically from Blasius solution within this very specific boundary layer, laminar boundary layer for incompressible steady flow two-dimensional case for this very specific boundary layer. Just give me a second. I would like to show you this table. Just give me a second. Let me find it from. I guess I have to find it from the web because I kind of forgot where it was in my which presentation was it. Just give me a second. Yeah, okay. I guess this is from one of the books. Let me display this for you. Let me get that. Okay, let me share it for you. Yeah, this one. Are you seeing the table?
Yes, sir.
Yes. So it says solution of the Blasius laminar flat plate boundary layer in similarity variables, which is basically eta versus f. And at every eta value, the solution, these are the solution values. At every eta value, we have f prime, and we have f double prime. Okay. And eta is listed all the way from on the wall, 0, eta equal to 0 is at the wall, all the way up to 10. So this goes outside basically the boundary layer. and it says in the small text here down here, it says eta is the similarity variable. So we have already seen that. And f eta function is solved using the Runge-Kutta numerical technique. And yeah, so f double prime is proportional to shear stress, f prime is proportional to u over u infinity, and f itself is proportional to stream function as we defined it in the class. So yeah, and the plot is basically, we have already seen it in the class. So these types of tables are listed in books. As I told you, I don't remember right now if it's listed at the back of your book. Maybe it is, or inside this chapter, maybe it is. But if it's not, you can actually find it over the internet anyway. Yeah. So this is how we make use of this Blasius laminar flat plate boundary layer solution. Good. So it's 3:02 right now. I will talk about another an extension of this topic, but we will have to stop a little bit early today because I have to go have my COVID vaccination today. I have an appointment. So let's go back, and I will continue with this with few slides that are relevant. I will go over these slides. You can you can watch this video and take class notes about this. Let me share it. Share my screen. Can you see the slide?
Yes, hocam.
Okay. So the next, let's say, the thing that we did not discuss, I mean, that is not included in Blasius boundary layer solution, is the fact that, I mean, the significant assumption was that there is no pressure gradient in the streamwise direction. And that happens mainly because of the fact that we have a flat body surface, okay? And as I told you, that indeed, that condition indeed can be generated in a laboratory environment. But in most real life problems, we do have curved surfaces, right? Simplest example is like the flow over an airfoil, for example. Whenever we have curved surfaces, of course, the pressure or the edge pressure is not constant. It changes with the streamwise direction. Edge velocity is not a constant, and edge pressure is not a constant. Then how do we need to actually can we still use some kind of approach like Blasius did and try to obtain a solution for that case? Okay. So here you're seeing some information here. If the boundary layer edge velocity is not constant along X, which means that the edge pressure PE is not constant along X. How do I say that? Because basically I can make use of the differential form of the Bernoulli equation. What do I mean by that? If the Bernoulli equation is in the let's say absence of, first of all, let me remind you under which conditions Bernoulli equation is valid and what was Bernoulli equation. Under the absence of, let's say, gravitational effects, Bernoulli equation says that along a streamline, P over rho plus U square over 2 will be a constant. Okay, I don't know if I can take notes on the slide. Let me try to get a pen. Okay, so P over rho plus U square over 2 will be a constant under the absence of, as I said, any gravitational effects. So now I have to, I mean, I would like you to remember this stuff from your fluid mechanics classes, because we discussed this in fluid mechanics in quite detail. First of all, again, as a reminder, this is a constant along a streamline, okay, for rotational flows. This is this quantity is a constant everywhere. First of all, when I said along a streamline, let's say between 2 points on a streamline, this quantity is constant. But for an irrotational flow, which is basically what we assume, for example, outside the boundary layer, for an irrotational flow, this quantity is constant everywhere between any 2 points in the flow. Okay, so this is from fluid mechanics information. The thing is, at the edge of the boundary layer, we indeed, let's say, have that condition. So basically, what we say is, if the edge of the boundary layer is just outside the boundary layer edge, we are in the inviscid region, or in fact we can maybe call it the irrotational region, then we can actually use the Bernoulli equation, because Bernoulli equation is not valid for whenever we have viscous effects. It's not valid, but whenever we are dealing with inviscid flows, at least along a streamline, this is valid. So the thing is, since this equation gives us a relation between pressure and velocity, and if we are outside or just at the edge of the boundary layer where we have minimal or no viscous effects, this equation is valid. So which means that I can take the derivative of this equation, and rho is a constant. So I can take 1 over rho times derivative along x. So let's say dp dx. So I took the derivative of the first term, plus I will take the derivative of the second term, 2 times u times du dx, and times 1 over 2, so 2 will cancel out, will be equal to 0 on the right-hand side when I take its derivative with respect to x. So as you can see, this equation is coming from this. So 1 over rho dp dx will be equal to minus u times du dx. But if we use the values at the edge of the boundary layer, so I can write u infinity, I can maybe write p edge here. So this equation is just the derivative of the Bernoulli equation, or the differential form of the Bernoulli equation for the edge of the boundary layer. So Blasius, in his first attempt, said this is 0, okay, and then we obtained all of the stuff that we did today. But the question is, what if it's not 0? Okay, what if we have a finite amount of velocity gradient on the surface? Then we see that if the velocity gradient is not 0, then this term will be not 0, okay? And then it will result in a variation of u with x as well. So if p is varying with x, if px is not 0, is different than 0, u ex will also be different than 0. So there will be, therefore, a pressure variation along x means that there is a velocity variation or edge velocity variation along x. Before I further move on, I would like to discuss the physics in this figure. Okay. What do I discuss? First of all, you are seeing, first of all, a curved body, a curved surface. So this is our surface here. And we have different stations. We have stations from 1 to 4. At every station, you see some velocity profiles. Now, if in the first station, we have a certain boundary layer profile, as you can see here, we have a certain u edge velocity. And if you look at the gradient of the velocity profile on the surface, so du dy here, you see that it is indeed positive. So meaning that velocity actually, velocity profile with this function, sorry, it gives a positive velocity gradient, which gives a positive wall shear stress and all that. So this is what we have seen. So the question is, as you move along x now, and if the velocity gradient is not 0, so which kind of shows you a more realistic case. The question is the velocity increasing or decreasing with x as I move along the surface? As I move along the surface, meaning that I'm walking in this direction, and if the velocity is the question is the pressure dropping or increasing as I walk along the surface. So if the pressure is increasing as I walk along the surface, this gradient will be, which means that it is positive. With increasing x, pressure is also increasing. So dp dx is positive. This case, so which means that I'm moving, or the fluid particles are trying to move along this direction, facing a progressively increasing pressure, which is trying to push them back, basically. Okay, this kind of condition is known as adverse pressure gradient. Adverse pressure gradient in fluid mechanics. Why is it, the word adverse means it's kind of it does have a negative meaning, right? Adverse, something that we do not want. Why is it why do we call it adverse, and why is it something we do not want? Because it means that fluid particles are trying to move against nature, because in nature, fluid particles naturally wants to move from high pressure to low pressure. That's how nature works. If you create high pressure, low pressure difference, fluid particles move from high pressure, low pressure. But here, if the pressure is increasing along X or along the surface, let's say, fluid particles are trying to move against an increasing pressure, which is not good news, because it means that the pressure increase along the streamwise direction could be so high that at some point it could basically block the fluid particles from moving anymore. Okay, so at some point on the surface, for example, it's indicated here, the fluid particles will stop moving in streamwise direction. Okay, and after this point, if you go further downstream, if you did some experiment, and if this adverse pressure gradient is strong enough, you can see that within a region in the flow, which is marked with this dashed line here, you will end up with fluid particles cannot move in positive streamwise direction anymore. They will start moving backwards in negative streamwise direction. So this point is called point of flow separation. The flow, if you remember, we have talked about flow separation very roughly before, but this is how physically it happens. At the flow separation location, the velocity profile takes a very specific shape. It does have mathematically what we call an inflection point in the function, inflection point in the function. So its curvature changes, as you can see, and the specific value of du dy, which we use it to calculate the wall shear stress, becomes equal to 0 right at the separation point. If you move further downstream, this du dy value even becomes negative, as you can see from the velocity profile, because of this negative reverse direction velocity field. So therefore, wall shear stress even will become negative. So it's a complex flow environment, but all the story that I kind of discussed right now is a possibility that can happen if you have an adverse pressure gradient on the surface. It depends on the severity of the adverse pressure gradient. If it's not severe enough, separation may or may not occur. Depends on the pressure gradient. That's what I'm trying to say here. The opposite of this can also happen, meaning due to different flow conditions, dp dx could be negative as well. So as you move along the surface along positive x direction, pressure can drop. So this is something fluid particles would like to have, because they naturally want to move from high pressure to low pressure. And if the pressure is dropping in streamwise direction, they will not be, that condition would be something fluid particles prefer, because it's something natural. So that's in fluid mechanics literature, we know this as favorable pressure gradient. Favorable pressure gradient, and the word favorable does have a positive meaning. So favorable means it's something that fluid particles favors, so something they would want. Okay. In that case, there is no, if there's a favorable pressure gradient on a surface, this separation is totally out of the question. There will not be any separation. Definitely, there will be a certain pressure distribution. Fluid particles probably will accelerate even more, and then so it's a very less problematic kind of distribution. Many of the problems we deal with in aerospace engineering over aircraft wings, over other helicopter wings, helicopter blades, over compressor blades in engines, turbine blades, not turbine blades, I'm sorry, compressor blades, we always deal with adverse pressure gradient. I said turbine blades, for example, in a gas turbine engine, inside the jet engine, we have turbine blades. On the turbine blades, we almost all the time have favorable pressure gradient. Okay. I don't know if you discussed this in the propulsion classes, but if you did not, probably you will see that detail next semester in propulsion too. But for compressors, helicopters, propellers, fixed wing aircraft, we always have, in most of the operating condition, we have to deal with adverse pressure gradient, which could generate those flow separation phenomena, inflection point in velocity profiles, negative shear stress on the surface, and all that. Okay. The question, so this is some conceptual and physical description, but the question is, under these dpdx values, whether we have a positive dpdx or whether we have a negative dpdx, how can we solve the boundary layer equations under that condition? Because Blasius did not show us how to do that. He assumed dpdx 0, so a flat plate problem, and obtained a solution. What if it's not 0? I will talk a little bit about that, and I have to stop in about 2 minutes. So now our topic is, if you noticed also here, is incompressible flow with pressure gradient. So generally, not generally, after Blasius obtained the solution historically, other researchers, and most of them from Prandtl's group, started to work on this issue and trying to obtain a solution for this case. And generally, in this case, we define what we call a pressure gradient parameter M, this M here, but based on this Bernoulli relation that we have seen in the previous slide, this relation here. And this pressure gradient parameter is defined such that, like this, that you're seeing here, x over u edge and du edge over dx, which is directly related to pressure gradient from the Bernoulli relation. And from here, there's a mathematical relation. If I take, for example, x to the left-hand side of this equation, m times dx over x, it will be equal to 1 over u edge and dx to the left-hand side, and I keep du edge on the right-hand side, so I can get an equation like this, and I can actually integrate this m times ln x becomes equal to ln u edge plus ln constant, and this kind of approach gives me like a power law type of distribution for u edge is equal to x to the m, bn and m being a constant. Now, if I invoke this information into our similarity solution, which I mean by the Blasius solution, again, using similar approach, defining an f function, using coordinate transformation, defining a stream function, and an f function similar to what we did before, we obtain a new ordinary differential equation for f. This new ordinary differential equation has extra variables, like we see the third derivative with respect to eta. We see again the first and the second derivatives here as the first derivative square here, and multiplied with certain parameters like m plus 1/2 and m, and here 1 minus f prime square. It does look different than our Blasius equation, and this equation in aerodynamics or in fluid mechanics is known as the Faulkner-Scan equation. Okay, but it is a more generalized case than the Blasius equation, such that if you take m equal to 0, okay, if m equal to 0, which means that there is indeed no edge velocity variation with streamwise direction, which of course means there is no pressure gradient. So m equal to 0, inserting m equal to 0 in this equation should reproduce Blasius equation, which indeed it does. So we get this as a flat plate solution. But we are not interested in that. We are interested in two cases: when m is not equal to 0, and then m could be positive, which corresponds to accelerating flow, which I described as, which corresponds to the physical case of favorable pressure gradient that we just discussed there. So there is indeed no risk of flow separations, as it is also indicated on this slide here. Or the second case, which is more detrimental or more dangerous, let's say, in terms of flight vehicles. When m is less than 0, we are indeed dealing with a decelerating flow, which means we do have an adverse pressure gradient and with a possibility of flow separation. So generally, the solutions can be obtained in this manner, and for example, generally for the specific case of for a specific value of m, which is equal to this number minus 0.0904, f double prime, which is actually related to the shear stress, becomes equal to 0. I will go back. Becomes equal to 0. And if you remember from our physical discussion, when shear stress becomes 0 somewhere on the wall, that corresponds to the separation point. Okay, and this Faulkner-Scan solution says for a laminar flow, again, still no turbulence, by the way, laminar flow, an incompressible flow, but now with pressure gradient. If this m parameter becomes equal to this number, that is your separation location. And if you are downstream of that separation location, further downstream in streamwise direction, you will end up with a separation zone. So this is kind of analytically how we predict, or theoretically how we predict the separation location based on this Faulkner-Scan, the solutions of the Faulkner-Scan equations. Okay, I would like to stop at this point because I am already running a little late. I have to step up and go to the hospital. But anyway, we will continue from this point in tomorrow's class. Okay? For the, just a second, for the incompressible flow with pressure gradient. So I will stop sharing this one and also stop the recording.